Let's find the gravitational potential at a point P outside a uniform spherical shell. The distance from the center O all the way to this point P is exactly r. We can divide the entire shell into infinitely many thin rings. Let's consider one such ring at an angle theta. To find its mass, we need its area. Let's give it a tiny thickness by adding a very small angle, d theta. This creates a tiny arc on the surface. Its length is the radius r times d theta, giving us the ring's width. And looking at the triangle, the radius of the ring itself is r sine theta. If we unroll the ring into a rectangle, its area is its circumference, 2 pi r sine theta, multiplied by its width. Finally, multiplying this area by the surface mass density sigma gives us the tiny mass of the ring, dm. Every point on this ring is at the same distance x from point P. So, the potential dV due to just this ring is negative g dm over x. To integrate, we need to relate the distance x and the angle theta. We do this using the law of cosines. Because r and r are fixed constants, differentiating both sides gives 2x dx equals 2 r sine theta d theta. This perfectly isolates sine theta d theta, allowing us to swap it out for terms of x. Substituting this into our potential equation simplifies things beautifully. The x cancels out completely. Now, we just integrate x. For the entire shell, x goes from the closest point, r minus r, to the farthest point, r plus r. Evaluating the bounds gives us a difference of exactly 2r. Notice that 4 pi r squared sigma is simply the total mass of the shell, m. The result? The potential outside the shell is exactly the same as if all its mass were concentrated at the center. And as always, thanks for watching.